Hi, in this video we were talking about generative learning with autoencoder and variational autoencoder. So let's go. First, I have a quiz for you. Which face is fake here? So these are whether it's a real person or an image that generated from a person who doesn't exist. So you can pause the video now and put your keen mind to work to determine which face is fake and which face is real. You can pause the video. Assuming you return from the video, and I hate to tell you, but this is a trick question because all of these faces are fake and they are generated by a generative model. So, what is a generative modeling? Right? Generative modeling is a process that take input training sample for some distribution and then learn the model that represent that distribution. And this process is under unsupervised learning. And also at the result, it can generate new sample from the distribution that look like the training data, but it's not from the training data. So these are what we refer as the fake data. So you can see here, if you see a bunch of example. What you generative modeling trying to learn is the underlying distribution. In this case, is a density estimation or the density functions, right? And for the sample generation, you can take in input data, and typically input data can be generated by some data distribution from your training data, but the generative example are generated by the model itself. So these are the generative images that look similar to the training data, but they are not exist in the real world. These are generated by the model. So why do generative models, right? So first thing is that really useful to learn some underlying variables or features, right? So for example, you construct generative model of training data can be used for simulation or planning. So for example, you can simulate some environment that does not exist using your training data. So these are great for simulation. It's also great for planning. So the image you see right here is the generated image of typical bedrooms, and this can be used for some purposes. You can think about Airbnb or some simulation, people trying to get decoration done and things like that. Generative model can also produce realistic sample of artworks. They do in super resolution, recolorization of images. See the images you see here that look like celebrity, but they really not. They are fake images that train from a celebrity data set. So they may look familiar to you, because they look like some celebrity, but these person do not exist. The third reason is the training a generative model can also enable some manipulation in what called a latent representation that actually very useful at general features. So for example, if you have a sketch of some object, and you're able to understand the underlying of the sketch, what is mapped to the real object, then you'll be able to generate very realistic image from just sketches. Right? So that's very, very powerful features there. Also, generative model can be used for outlier detection. If you have a problem how do you detect whether you run into something novel or something rare, right? So that's where outlier detection can be important. And the strategy is you can leverage generative models, and you can detect the outlier in this generative distribution, and then you use the outlier to improve the training even more, right? So let's take an example of a collecting data for a maybe self-driving car application, right? So if you collect data from a real world, it's typically gonna example a Gaussian or the normal distribution, where many of the data sort of right in the middle, and typically, or actually 90% of the driving data is gonna be on the highway where the weather is sunny, and typically on the pretty straight highway or straight road. So, well, these data is actually not very helpful to train your automatic driving vehicle, because it's just too easy, right? Just going straight, and that's what it is. So what you really concentrated in the data at the edge of the distribution, the outlier, the way out. And these data typically is very unusual images, but they're going to be very necessary for your training. For example, you can see here some edge cases where it's unusual, right? You have a big plane in your picture, the roads are curvy. You have some image of harsh weather with raining and limit your vision. And you also have an image of like a pedestrian certainly crossing the street. So this outlier can be used to avoid unpredictable behavior when you train in the model. So it's very important for that you don't oversample this data in the middle, but you make sure you sample or oversample the data on the outlier so you can build a better data set. All right, the three topical type of generative model is autoencoders, variational autoencoder, and generative adversarial networks. So we're going to talk about two of them today and the third one for the next video. So let's talk about autoencoders. What is autoencoder? It is an unsupervised approach to learn a lower representation or a dense feature representation called the latent space from unlabeled data, right? So because it's unsupervised. So you can imagine if you have an image or some fixed size vector input, and you want to learn the latent space or the dense present representation of this input space. In this case, Z from these unlabeled data. So you just an X, you don't have a Y. So you can build a neural network to compress the representation of X down to Z, right? And this, by the way, this we call a encoder. So the encoder is a neural network that learned to map from the data X to a low-dimensional latent space Z, right? And then you may ask, well, why do we care about the low-dimensional Z? Well, there is a few reasons. Number one is that Z actually represent knowledge, the compact representation in the input data, right? So to think about X here is a very high dimensional data. And typically, I mean, we are trained as human to look at this image and say that is a 2. But if you think about it, it's just a series of pixels. It does not represent a 2. So this low-dimensional Z actually contains some dense representation or knowledge that's saying this is a 2 somewhere in there, right? So Z's are very important to extract knowledge from the data. And also Z is a compact low-dimensional. You can think about it as a form of compression, right? And number 3, as we find out later on in the videos, is by manipulating Z, we might end up with some very interesting visual analogs of the real data. So Z's are quite important. All right, so how do we learn this latent space Z, right? So how would we train this encoder model to make sure that it learns on the right weight to compress down to the original data down to Z, right? Because you don't have any label of Z, right? No human can actually present the label for Z. So how do we gonna train this network, guys? And this is a trick. We're gonna use a mirror neural network that basically mirrors the encoder, and that's what's called the decoder. So the decoder is a neural network that learns the mapping from the latent space Z to a reconstructed data or observation X hat here. Because the reason it's called hat is because it's an estimation, it's not the original data, right? And so this represents maybe a blurry image of a 2, but nonetheless it's a 2. So this is from the latent space. You can reconstruct some observed input. Okay, so you can then compare X and X hat, right? Compare these two, and using a loss functions like a square loss here in this case, right? So you can use the square loss to compute error gradient and pass it through the network and learn all the parameter updates for both of the networks, right? That seems pretty straightforward, right? But notice one thing is that both of the loss function here, both of the input is X, so we don't need any Y. So this one does not need human supervise. It can learn on its own, right? Taking input data, unlabeled, construct it all the way, and then compare and to find the errors and then update the gradients. Pretty cool. Now, there one thing important is the dimensionality of this latent space. And this dimensionality actually going to determine the quality of the reconstruction. Right? So I'm going to give you an example here with the MNIST data set. And just depend on the dimensionality of the reconstruct the latent space. So if you use 2D, so think about it, you're going to compress that 28 by 28 image down to only 2-dimensional, and then use that 2-dimensional, which is only like 2 number, and then reconstruct that image back. And now you're looking at the image, you can actually see the image pretty good, right? But it's a bit blurry, right? Because you only use 2 number to really construct it, the whole image. Now if you use 5D, then you having slightly better results, and it look a bit clearer compared to this ground truth with the original image. So a 5D look pretty good. So apparently all you need is only 5 number to be able to reconstruct every single pixel in this image, right? So you can think about encoding is a form of compression, right? You can get it down to like 2D from 700 and something dimension. And a smaller bottleneck layer Z will force the network to learn a tighter, more compact latent representation of the latent space. Okay, so autoencoder is for representation learning. And, the bottleneck hidden layer Z will force the network to learn a compressed latent representation, as you see before. And the reconstructional loss will force the latent representation to capture or encode as much information about the data as possible. That's the whole point of this autoencoding, right? So autoencoding also means automatically encoding the data. Okay, so as far as the implementation, we can stack autoencoder in a sort of hour shape neural net, right? So this architecture typically symmetrical with regard to the bottleneck layer, with this case or hidden 2 in this case. I'm sure only here like a few layers, but you can add more layer to encode even more complex coding representation. And these are symmetrical, right? So you have hidden layer, your Z only have 30 neuron, whether your hidden unit 1 and 3 have the same number of neuron as 100 neuron. And then you have an input layer, have 784 unit. Why? Well, because that's the dimension of the input, right? Remember MNIST, 28 by 28 dimension. And so you have a output only have 784 unit to reconstruct the image with the reconstruction, right? So the latent space or the coding here would be produced right after this hidden layer 2, right? To produce the coding, right? So that's your stack autoencoder. How do you implement it? It's simpler than you think, right? So you have a encoder and the decoder as separate sequential models, and you can use Keras model sequential here. You flatten the input, you have a couple of dense layer with 130 neuron, and you use activations scale ELU to add your activation. And then with your sequential model for the decoder, you start with 100, and then take input set for 30 because that is your latent space. And then from 30, go to the original dimensionality space, which is 28 by 28. Now, keep in mind here, my activation is sigmoid. Why? Why my activation is sigmoid, not softmax, right? The reason it is sigmoid because you want to map all of these value into between 0 and 1, which is a grayscale value, right? Because you want to reconstruct it or in this case, a grayscale image of the MNIST data set. So that's why sigmoid. Typically, sigmoid also construct a little bit faster as well. And then the autoencoder, AE here, it's just the sequential model of the encoder and the decoder. Told you that was not too bad, right? And then you do some other things like you had to figure out what is the loss. The loss here is not MSC, but it is binary cross entropy. And the reason is binary cross entropy is that you actually calculate it like a two class, 0 and 1, which is a extreme pixel, right? From 0 to 1. And what the model produces is, think about it like a probabilities of a pixel being a 1, right? So it is a probability, and you have sort of a binary 0 and 1, so therefore it's binary cross entropy loss. And binary cross entropy loss perform a bit faster than MSE, and so we prefer to use it. And then you use SGD with learning rate 1.5. Now, to train this model, you have the call fit, just like usual. You feeding, guess this, you're feeding X string and X string. Remember, because you want to compare the training data with some reconstructed data, right? So this second X string is to you to compare it with the reconstructed data. So that's why you have two X string here, not the Y string, but the X string. Right? Okay, and same with validation data, X valid, X valid. Cool. Here's the result. This is your input image from the fashion MNIST. These are the constructed images, and you can see here the example of these objects, and it's recognizable as a bit blurry and lossy. And so, you can train a more complicated model, make your encoder a bit deeper, and hopefully you come up with something better, right? So why don't you go ahead and go try and see what happens, right? I won't spill the result for you. You can try it. Right? See if you get better result in what I have up here. All right. Another really cool thing about AutoEncoder is that you can actually doing unsupervised pre-training. And this is taking advantage when you have really small number of labeled data, but a huge number of unlabeled data, right? So what you can do is you can take all this unlabeled data to train an autoencoder. And then what happens when you have really good autoencoder, you can copy about half of the network from the hidden latent variable into the earlier. And then from there, you can train your supervised learning with the label data. And this is because the network parameter already trained here, then you have a more robust network than training from scratch. So it's pretty cool. You utilize both unlabel and reuse some of the layers that you trained previously. All right, so that was autoencoder. Let's now talking about variational autoencoder, or VAE. So what is the difference? The difference was actually quite small. So in autoencoder, you're trying to estimate variable z. In variational autoencoder, instead of directly estimate z, I'm going to estimate the distribution of z. So in that case, I'm going to estimate a mean and the standard deviation. And from there, I can sample z instead of learn it directly. Now, why does it matter if I sample? Because now, instead of have a fixed representation, now my autoencoder actually have a probabilistic model into autoencoder. And let me explain why later on, that this actually worked better into the reconstruction of the images. So yeah, you sample from a mean and a standard deviation vector to compute the latent space. Okay, so what about the optimization? How are we going to do this optimizations, right? So your encoder going to compute the probability with parameterized by fees here, which is the parameter network, a network parameter that the probability of C and Z given the input data X. And the decoder going to compute something quite the opposite with parameterized by different parameter, network parameter thetas here to compute the probability of C and X again given the latent space Z. Right? And the loss functions similar in the reconstructional loss, but we're going to also add the regularization terms here. So the loss before is MSE, but the regularization term may need some more explanation here. This is a calculation of what called a Kullback-Leibler divergence. So this is the difference between two probability distribution parameterized by phi, which is the encoder. So you want to see how much this one different from the a prior distribution. Typically, this one is set at a standard normal. And the reason we have the regularization term is so that you can sample from a more random distribution instead of focus on sample one stop at the time. So it create more variational to your encoding. And that's what why the name variational come into place, right? So this regularization term trying to keep that variation sampling in check. Now there is a little problem to this approach, and it's nothing to do with this one, but rather to do with the backpropagation of the gradient. And this little layers here is a problem because instead of having deterministic model, you now have a sampling model, a stochastic model, right? So let's look into how's it causing problem, right? So if we had to think about, okay, we can't really propagate the gradient to something that are random, right? You need a specific function. So instead of model this from a normal distribution, I'm not going to do that. Instead, I'm going to put a reparametrization trick on this z, okay? So consider my z going to be just a sum of a fixed vector mu and a fixed vector sigma scaled by a random constant epsilon that draw from a prior distribution, right? So the formulation is going to be this. So now z become a bit more deterministic, right? Because this is the fixed vector that is also a fixed vector scaled by some constant, right? So I can calculate z directly here, which, you know, some epsilon that draw from this prior distribution, right? So what happened here is before you have deterministic node when you do backprop, but you have the sampling layer z here that you can't really do backprop because it's stochastic or is non-deterministic. So what happened here, now that if I were to be able to calculate z at a functions, right? So now it becomes deterministic because now z gonna be reparameterized by mu and epsilon, and you know, it's a function of these things, and epsilon, which is still a sample layer, but it at least now it get pushed to the sides. So what happened is when I run backprop and I run a gradient of the function f with respect to z is deterministic because you can take in the derivative of that simple function I showed you earlier, so you can calculate the gradient and pass the gradient back and forth in the function. So the trick is similar to the recurrent network when you trying to make the gradient path a little cleaner, and you're trying to make this gradient propagate a bit smoother, right? So that was a reparameterized form of the backprop of VAE. Okay, so VAEs really cool when you start manipulating or perturb the latent representation, right? So let me explain. If you keep all variable fixed and start changing or slowly increase or decrease a single latent dimension, what would really interesting happen is that it start producing some noticing visual effect of the changing of that particular latent variable, right? So what it means is different dimension of z actually encode a different explainable, interpretable latent features, right? So if you look at this bottom row real quick, these are, if you look across, these are showing different head pose of a person. And these images are fake images that are generated by just changing one dimension of the latent variable z. So z is a vector, so you change only one numbers in that vector, and that would produce, when you reconstruct the image back, it produce this head pose changing characteristic, right, which is really cool. And you can, to keep in mind that you keep everything else the same, like all the z stay the same. That's why this is very similar images, right? Now, you can do the same with the smile factors, right? So you have go from no smile at all to smiling, right? with certain head pose. So this way, you keep the head pose the same. You only change the smile factor, right? Now, ideally, we want the latent variable to be uncorrelated, right? So head pose here and smile here are uncorrelated. It respond to very different effect on the image, but typically or ideally, you want these latent variable to be unrelated because they're supposed to be compact, right? So if they are still correlated with me, I can compact them a little bit more until they no longer correlated, right? So you can reinforce this by enforce a diagonal priors on the latent variable. What will happen is it's trying to be more correlated to itself instead of other variable, right? Which encourage independence. And so this in overall called a disentanglement process in latent space. Right. We're not gonna have enough time to go into details of that, but just so you know. All right, application. We're going to use a very interesting data set called the Celeb A data set. These are the collection of over 200,000 color image of celebrity face, along with the various label like wearing hat and smiling. I know we're talking about unsupervised, so we don't really need label, but we might need it for some other interesting purpose, right? So some analysis on VAEs here from a paper by Hugh and others, we can reconstruct the input image, right? So these are the color image that we're able to reconstruct. So these are the original image, and these are the image we was able to construct. You notice that the reconstructed image seemed to be a bit blurrier, and that makes sense because there is some, you learn from a very compact latent space, so there is some smoothing going on there. So typically, think about it's like an average images operation, make things a bit blurrier. But you can see a lot of resemblance, so closer this reconstruct image closer to original image, it means that, we reduce the errors by quite a lot. So you're trying to minimize this errors here. But you can see these images still a little bit blurry. You can tell that's not really taken in the real world. So, there is certainly have some loss going on there. Now, another interesting thing is that you can still learn, generate brand new image from the same latent space or the same VAE model, right? And these are the brand new image that we now be able to generate. Right? So it's color image of a face, and we're able to just crunch that out on demand. I thought that was pretty cool. Now these image are, even though that's a person, I mean, many of them pretty good looking person, but these are all fake, and you kind of tell they are fake, right? I'm not gonna fool anyone. But later on though, I'm gonna show you some of the image that you can't even tell that's fake, and that come from another type of generative learning. Just tease you a little bit there. Okay. Well, one more thing I want to show you is the manipulation of the latent space, and this you might like this. So you can perform arithmetic on the latent vectors on the latent space that has some visual analogs to the decoded when you decode it back to the original image. And the arithmetic can be like, you have an old value of z, but now you want to manipulate it. So what you do, you can add some attribute to it. So you can add like a smiling attribute here, right? You have another z vector that focused on smiling. So you're going to add that into your old z vector to get a new z, right? And then you have this hyperparameter alpha to determine how much of this attribute you like to add, or how much the smiling factor you want to add to your z. Now the question is, where do you find the smiling vectors, right? So this turns out that with the Celeb A dataset, come with many metadata with label with the attribute. One of them is smiling, so you can learn this smiling vectors from that label metadata, right? So it turns out you can learn all kind of factors: smiling, blonde, male, female, eyeglasses, and so on and so forth, and determine on the value of alpha here. You can either subtract the new z, or you can adding to the new z, right? But you're changing alpha here, and as the result, the reconstructed image have very smooth and beautiful effect on this Celeb A's data set. So you can see like smiling, you go from just original image or the no adding of any factor. So this is reconstruct the image with no adding of this factors, or you can subtracting the smiling factors, so become really proud face, and you can add the smiling factors, so on and so forth. You can do it with the blonde hair, with more face on the male feature or female features, having eyeglasses, so on and so forth. So it's really cool stuff, right? Well, so that was it. In summary, we just talked about the compressed representation of the visual world. Reconstruction allow for unsupervised learning, could require no label. You can do some reparametration trick for end-to-end training for variational encoder. You can interpret hidden latent variable by using perturbation. And finally, you can generate brand new examples. So if you thought that was cool, wait until next time when we cover generative adversarial networks. Looking forward to see you then.